4EF. 4EF relies on the fact that you did the previous exercises. So we had one exercise that covers all of quadratics. Then you had one exercise that covers pretty much cubics, right, which is our last session. So today is just running on with that idea that if you know your theories well for quadratics, cubics, well then you can now do what that quiz was really doing, was to analyze even powers versus odd powers, which we covered previously as well. So what are some tips for E and F as you're doing them? Very short exercises. Look for the number of x-intercepts an equation has. Why? Because that tells you the kind of factor you're going to get in the expression. So in the equation, you could get 2 factors or 3 factors or 4 factors, and what type of factors depending on the type of x-intercepts. One of the things we know is that quadratic factor, the graph has a turning point, which is that question 1 quiz that you guys were doing before. I was looking at, I saw a repeated factor, so I knew I had to have a turning point. And then if you have a cubic factor, okay, then you expect an inflection point. So if you don't know what a quadratic factor and a cubic factor is, this is what I mean. If you get y equals to x plus, say, a squared, that's a that's a quadratic factor. If you get a cubic factor, it'll be something like y equals to x plus a cubed. Then you know at x equals negative a, there should be an inflection point. Whereas this one, for the quadratic one, that means at x equals negative a, I expect a turning point. Okay, you can play on Desmos. Try putting in some numbers and you'll see every time it's an even or odd, it changes whether you have a turning point or an inflection point. If you have a linear one, so for example, something like this, x plus b, x plus c, x plus d, they're all linear. Because they're all linear, I expect it to cross at these x-axis intercepts. So at negative b, negative c, negative d, it should cross. Hence, this is a cubic graph. Because the only way to cross 3 times, when you draw it, that's what a cubic graph looks like. You just don't know whether it's positive or negative. So it could have been the other way around. 1, 2, 3. Okay? So your job is to look at the number of x-intercepts and then determine what's roughly the graph looking like. Here are some patterns that you can see, and hopefully from exercise 1G, and also, I think there was another one. Yeah, 1G was the main one. I try to get you to explore the different powers. And we can see that the larger the power is, but it's even, squared to quartic, they're all symmetrical. That was one of the things I mentioned to you, whereas odd powers are asymmetrical, right? So if I gave you something like this now, here we go. I'm going to give you 30 seconds. Using the skills I taught you from number 1 before and also repeating it here, what does this one roughly look like? Just have a guess. Draw it in. So on your sheet, I gave you an f of x equals to x plus 1 times x minus 2 times x minus 1 cubed and then x plus 3 squared. So this is a, to the power 5, 6, 7. So it's a septic polynomial, order 7, a degree 7 polynomial. Okay? What does this graph roughly look like? Roughly. I could have made it a bit trickier by changing one of the brackets there, but I'm going to keep it here. Actually, I'll ask you the follow-up question after this one. Have a guess. What do you think you know? For those who don't know how to start, we can already see this is an x-intercept at negative 1, x-intercept at 2, x-intercept at 1, x-intercept at negative 3. So I'll put all the points in for you. Negative 3, 2, 1, negative 1. So we know that the graphs have to cross, touch, something about these points. All right, here we go. That should be more than 30 seconds already. So what do we see? At x equals to 1, I expect an inflection point because it's a cubic factor. At x equals -3, I expect a turning point. Okay, so turning point at -3. Now, what I don't know is whether it looks like this as a turning point or whether it looks like this. Okay, we do know that it has to cross through -1. So let's take the upper graph. Let's say I went like this. Turning point crosses through -1, crosses through, where is it? No, inflection point at 1. So it will look something like this. Inflection point at 1, and then it crosses through 2. That's one way of looking at it. Versus, I'll draw the blue version. Turning point at -3, crosses through -1, inflection point at 1, and then crosses through 2. Which one is the correct answer? Green or blue? So number 1 or number 2? Because only one of them is right. And there's many ways to figure out definitely which one is correct. Vibha. Very good. So that's one of the possible ways to figure it out. So number 2, the blue is correct. How do you also know? Well, find the y-intercept, because clearly the blue and green differs by y-intercept. Sub in x equals 0, and you'll know. That is one way to definitely check. What's another way to check?
There's no reflection. It's an odd function, and for it to be extending infinitely in the like negative x quadrant. So if it were to extend infinitely upwards in the negative x quadrant, it'd have to be reflected.
Very good. It's very good. So one was y-intercept, which is what Vibha was saying, and the second one is what I looked at. And this is what I said, that I could have changed this question to see how many of you picked up which one's the correct answer. See, all I had to do to really test your understanding was if I swapped one of these brackets and I changed it to 2 minus x instead. You'll still get the same intercepts. But by me changing 2 minus x, if you actually expand the brackets just on the x times a negative x times an x times an x, you still get x to the power of 7. The difference is one's positive and the other one's negative. And this is going back to your understanding of even powers versus odd powers. I said it's asymmetrical. One of the things that you know about cubics is that when it's x to the power 3, it's asymmetrical, but as you move to the right, the graph should be increasing. That's a positive cubic. If it was a negative cubic, the more you go to the right, it should be going down. So hence it looks like that. Okay, so if this is x to the power of 7, it's an odd power. It may look a bit thinner in the center, but the point is, overall, it should still be growing, which is what Zach was saying. So as you go to the right, the graph should be increasing. So in x to the power of 7, I know this is an x to the power of 7. So which one of the two, as I'm going to the right, it's definitely increasing, definitely blue. But let's say I'm still skeptical about it. That's when I would use what Vibha said. Sub in 0, see what the value of my y-intercept is. Is it positive or negative? And that I would be able to say what the graph roughly looks like. Okay? So that's the main skill of 4E and F. That one question is what I want you to take out. Okay, so being able to analyze those factors to predict x to the power of 32 or 37, you can still figure it out. Yeah? That's the idea. All right, team, flip over the page. All right, so what I taught you there was an intuitive way of looking at an equation and then determining what the graph looks like to analyze it, right? But when you're doing your SACs, and sometimes in your exams, they will say justify your reasoning. And you can't say what I was kind of saying. It's like, well, you kind of look it to the right and you can see that it should be increasing. It's not a really refined way of explaining it. I'm doing it so that you understand how to analyze, but then you have to prove it somehow. One of the ways that they want, when they say justify, you see that command term, especially for a graph, justify that you have a stationary point at whatever, or state obs, or justify that you have a local minimum at wherever. Don't just rely on saying yes because the derivative is 0 at that point. Okay, because if derivative 0 is just the stationary point, doesn't mean it's a local minimum, doesn't mean it's an inflection point, and doesn't mean it's a local max. So what you have to do is, this is the annoying part, you actually have to do a sign diagram or some sort of diagram to prove your point. And when you do a sign diagram, don't do this. And what's interesting, we do it really well at VBank. Last year, our group did this type of question justifying really well. So we had like into the 80s, 84% of us got it correct, whereas the state was in the about the 50s to the 60s. It is because a lot of students do this mistake. So don't be the statistics. When you're doing a sign diagram, for example, if I gave you something like this, y equals x minus 2 and x plus 2. You probably already have a visualization that's going to be a minimum. If you did a sign diagram table, what students shouldn't be doing is this. So then they shouldn't do -2, so they got their x-intercepts, -2, 2, okay, and then you do your derivatives for at x equals 0. Don't do this. Don't do that as a sign diagram, because you already know it's a minimum, and sometimes they say justify that's a local minimum. They already told you the answer. So you doing this, writing a derivative sign diagram saying, oh yeah, it's a minimum, doesn't really show that you actually know that it is a minimum. You're just regurgitating what they just told you. So the next step is you must actually write in the value. So what is the actual value, or the actual dy dx value? Don't just draw the signs. You actually need the values in there. Examiners will penalize you if you don't prove that this is actually a negative gradient, 0 gradient, or a positive gradient. You actually have to do that. So since we're not at derivatives chapter yet, so this one, you actually have to sub in the values. So if we're choosing, so this graph, x plus 1 has an x-intercept at -1, has an x-intercept at 3, has an x-intercept at 5. Okay, so those are my 3 x-intercepts based on this. I'm looking at this graph, x times -x times x. I know it's going to be cubic, but a negative cubic. So I know it has to look something like this. As I go to the right, it has to go down. So I know that. But I have to justify this. Right? Just because I know it, I can't say, yep, because this is a negative cubic, it has to go down. I can't say that. I have to prove it. So when you prove it in a sign diagram, we've got to test now, okay, when it's less than -1, is it true that the y value is positive? Now, I know it is positive, but you can't do this. You can't do positive, and you can't say, well, I already know x-intercepts here is 0, 0, and 0, and then say between -1 and 3, pick a number, and then you say, yep, it's negative, positive. You can't do that. So you can't say this is a positive 0, or like to draw out the sign to actually say that. You actually have to put in a number. So here, you need to pick a value. Say x is -2. Sub in and find f of -2. In this case, f of -2 would be -2 minus +1, 3 minus -2 times -2 minus 5. That gives you 1 times 5 times -7, and that gives you -35. That is what they want to show, because then that shows that you've calculated it. That's why you know the sign. Wait, what? Did I do something wrong? Should be positive. That's 1. And then -2. Oh yeah, you're right. Thank you. -2 plus 1 is -1. There we go. So then you can say it's a positive sign. Okay, so when you're using a justification, the tip is, and our ViewBank College students last year definitely have done what we've been training them to do. When it comes to justifications, as annoying as it is, you must actually do your calculations to prove, because it's a justify, especially if they say justify that this is a particular type of look. Okay? So how do you do a sign diagram? You can do, if you haven't done sign diagrams from last year, this is what a sign diagram looks like. So you have a plus, minus, like this. And all you do, is that you put in the value. So 1 less than -1. We've got now sign is positive. We've proven it. It's positive. So you draw a line up here. When it's 0, draw a line here. And then when you have negative, you draw a line here. And eventually, essentially, you get the shape of the graph through that. Okay, and that's how you can see the rough shape of the graph. And that's what they call a sign diagram. Okay, but you can do it anyway. You could have done it the way I've just done, plus, minus, and then draw out your shape. So you can say plus, 0, minus, 0, plus. It's up to you how you want to do it. But the point is when you're justifying, this must be available. Cool? Here we go. This is the graph, which I've shown to you, our prediction. That's the actual graph. The proof is here. You don't use derivatives until we get to the derivatives chapter. I think it's chapter 9. You only use them to find turning points. So for now, they're only asking you to justify the shape of the graph. And I have taught you how to find it intuitively and analytically. But if they ask to justify, please make sure taking those steps. It is a bit longer, but you have to do it that way if they're asking for justification. Usually it's 3 marks. Okay, marks should tell you the number of steps that you should take. All right, team, that's it for exercise 4E4F. Summary of that is just to be able to read a graph or read an equation and then visualize the graph. That's the idea. Okay.